record. All right, before we get started into the ANOVA, does anyone want to bring up anything about the past chapters and the taking the test and homework or anything like that? No, we good? It's so quiet in here. Okay, well, I guess we'll go into ANOVA. Let's see. So we've already seen how to do t-tests, and all the t-tests we've learned so far are how to compare the averages of two groups. The one sample t-test is when our other group is a historic average or some hypothesized group, but we were still seeing if there was a difference in the average. We are going to still stay on that same trajectory of looking at, do these groups differ in terms of the average of some score? Do groups differ? The big bonus we get when we move from a t-test to the f-test, the ANOVA, is we're no longer restricted to only having two groups. Now we can have more than two groups. So let's see, I want our pictures to still be here, but try and make them a little smaller so you can see the whole slide. Maybe not. Okay. So here's an example. Dr. Vito randomly assigns 30 individuals, so 30 participants have signed up to do the study, and he puts them into three groups, randomly assigns into three groups, evaluating two new approaches to therapy compared to a standard kind of therapy. So here's the new thing. Instead of just having a treatment and control group, we can have two different treatments and a control, or three different treatments. So he has the participants have been matched on anxiety and depression mood at baseline, and the thing that he's going to compare after 3 months is their Beck depression inventory and the Beck anxiety inventory. So he's going to compare some scores at the end of 2 months. So again, the new thing here is we have three groups. That's not going to work. Here's another scenario. Dr. Kreff wishes to assess differences in the oral word frequency among three groups of participants. There she is, yay. Those that have a right hemisphere stroke, those with a left hemisphere stroke, and then healthy controls. And he's going to compare, or she, the CAWA test, and have 20 participants for each of these groups. Now, the first example we would call an experiment, because it was the researcher who designated who went in which group, hopefully randomly. The second scenario here is what we would call an observational study, because how was it determined who was in the right hemisphere group instead of the left hemisphere group instead of the control? Did the researcher make that choice? No, it was outside of the researcher's control. It wasn't really a choice. It was just something that happened. It was an observation. So the second one here we would call an observational study, but we still have three groups. The top one is an experiment in which we have three groups. They both can be analyzed with an ANOVA because we're comparing three groups, whether you randomly assign them or observe them to be already existing. So there's some vocab we need to go over that are specific to this kind of research. So the experimental design, experiment refers to assigning the levels, and the grouping is what we say manipulated. Manipulated is when the researcher is the one to make the designations, hopefully randomly. That's an experiment. Versus an observational study is where the groups are not. They are pre-existing or observed. Those are differences in the experimental design, but they can be analyzed the same way, whether they're randomly assigned / manipulated or pre-existing / observed. Still, that's just a design. The data can still be analyzed the same way. Fixed versus random is some terminology that comes up when we have multiple groups. Fixed effects or fixed design are where we have all levels of a factor. So we talked about In R, when you have a categorical variable, you call it a factor. So factor in a lot of ways just means a categorical variable, and it's usually a grouping variable. So if I'm comparing my groups, and I'm doing like the first example, we have 3 different kinds of therapy, the 2 new therapies and the standard therapy that's been going on for a while. We have all 3 possible therapies as far as this experiment goes. So that would be a fixed factor with 3 levels. The 3 levels are new treatment 1, new treatment 2, and standard treatment. In the second example, we would have a 3-level factor for type of stroke or hemisphere damage. We have left hemisphere, right hemisphere, or neither. Those are the 3 levels of that fixed factor. So the factor of hemisphere stroke damage has 3 levels, and those are all the possible levels. So we talk about the grouping variables, often we'll call them a fixed factor, and we'll want to talk about a fixed effect. Another word that you'll see floating around in ANOVA literature and talking about ANOVAs is a random factor. A random factor is a categorical variable that we don't have all the levels of. We have a random selection of all possible levels. And in ANOVA work, this is rarer to come across, but if you have random effects, it's often more flexible to use not mixed ANOVA, but to use what's called multi-level modeling. And I teach a whole course on that, but I want to bring up the distinction. In the studies that we talked about the first today, those 2 different scenarios, the random factor would be the subject. In the first study, how many subjects were there? 30. There are 30 subjects. Is that all possible subjects or participants? That's just the random subset that we have in our data set or in our experiment. And they are going to stand in, these 30 participants are going to stand in as a random subset of all possible participants. So the participant or subject is a random factor. We could have a different set. But the therapy types are the specific ones we want to test, these 2 new approaches and the standard approach. So therapy is a 3-level fixed factor, and subject or participant is a 30-level random factor, is the way we would say the language. In the second scenario, our fixed factor is the hemispherical damage, right, left, or neither. Those are all 3. That's the complete listing of all options. So that's a fixed factor, a 3-level fixed factor we would for the side of hemisphere damage. Participants here, how many participants do we have in the second scenario?
20.
20 in each group for a total of
40.
30. No, 60. 3 times 20 is 60. Are those all 60 participants who this would apply to? No, that's a random, well, hopefully random, or at least representative subset of all possible participants. So subject is often called a random effect. Now you can have other random effects. Don't get too concerned, but if you're doing an education research where you have students in 2nd grade classrooms and you have 6 different, or maybe you have 16 different classrooms. And in that case, your classrooms are a random subset of all classrooms, and your students are a random subset of all students. You'd have 2 random effects, subject and classroom. To be able to have multiple levels like that, you have to go to a multi-level modeling. In ANOVA, you can only have 1 really random effect, and that's your participants. And that's a limitation of ANOVA. Works really great for a lot of stuff, but it is a limitation. So we can have 2 major kinds of distinctions of our factors in our ANOVA analysis. You can have independent or repeated measures fixed factors. Independent factors are also called between subjects factors, and this is where everyone gets only one level. So for the first scenario, the type of therapy the participant gets, they either get standard or the new one or the new second one. They only get one type of therapy. So therapy is different between the subjects, so we would call it a independent or a between subjects factor with 3 levels. In the second scenario, the independent factor would be type of hemisphere damage. In that scenario, people either have a left hemisphere stroke, right hemisphere stroke, or neither. We don't have anyone with both in that study. So that's our independent between subjects factor. Now, in this chapter and the next 2 chapters, I believe, chapters 12, 13, and 14, all we're going to deal with are independent between subjects factors. Then when we get into chapter 16, 15 and 16, we get into what are called repeated measures factors. Repeated measures factors are one in which every participant has every level. So this would be if we're doing like a pre-test, post-test. Time is a repeated factor. Everyone has the first time and everyone has the second time. So we have multiple levels within the same person. We aren't going to talk about those today, but that's the terminology, vocabulary that's associated with it. So today we're going to do experimental designs that are assigned or manipulated and pre-existing observed, but we're only really going to worry about fixed between subjects factors. Later on, we'll do fixed repeated measures factors. And in this class, the only random factor we will deal with is subject or participant. If you have something more complex, you need to go to a multi-level model. Questions about these terms? Okay. Now, our factor is a grouping variable. Do I need to make this so that it's not, can you guys see the slide, or is it overlapping with our pictures for you guys too?
Overlapping.
Overlapping for you too? Let's see if I can make this so that it's not so overlapping, but as bigger as possible without getting it overlapping. Let's see. There, that a little better. Okay, so in these scenarios we've talked about so far, our groups are very distinct and they were non-ordinal. But what if our groups were first grade, second grade, third grade? Subjects would either be in the first grade or the second grade or the third grade. That's a grouping variable, but it is also highly ordinal, first, second, third. And treating it as a categorical variable in an ANOVA ignores any ordinality of the levels. And I think that this is something that's often skipped over in undergrad stats, that if you have a categorical variable that has an ordinal nature, doing an ANOVA ignores that information and is a less powerful test. Instead, you should be doing like a regression and treating that variable as a categorical variable, perhaps. Or there are other kinds of tests that can take that ordinal nature into account, but I would really point you towards regression. So ANOVA is an abbreviation for analysis of variance. And I already said we can use it for experimental, quasi-experimental, or observational research. It has lots of different names. Usually it's ANOVA, but today we're going to do one-way ANOVA. This chapter 12 is one-way ANOVA. It's also called, there's a lot of different names for it. I'm sorry, people call it a lot of different things. They call it single factor ANOVA, univariate, uni meaning one, simple ANOVA, because it's the simplest situation you can have as one grouping variable, independent ANOVA, because we have independent groups, or between subjects ANOVA. All of these phrases mean the same math. All of these are where we have one dependent interval ratio continuous score that we're going to assume to be normally distributed, and we're going to have one categorical predictor or grouping variable. that can have 3 or more levels. The number of levels our factor has, the number of groups, we use the letter K to represent it. So K is the number of groups. K is going to be in a lot of our formulas. So in both of the scenarios I started class off, both of those had K equals 3 groups, whether they were left hemisphere, right hemisphere control, or new therapy 1, new therapy 2, or the standard therapy. 3 groups in both of those cases. Again, with ANOVA, we can have more than 3 groups. We could actually have 2 groups, but it like simplifies to the t-test. So we usually use ANOVA with 3 or more groups. A word that we often use for ANOVA is omnibus. Omnibus means overall. It's an omnibus or overall test to see if any of the groups are different from any of the other groups. It is more powerful, but it only tells us that our conclusion will either be no evidence that any groups are different or evidence that at least one group is different. It will not tell us which group is different or if there are multiple groups that are different. To be able to tease that apart, we have to do post hoc t-testing. And that's what the next chapter is all about. But the F test, the ANOVA test, is just looking at overall, do any of these groups differ? Jump in whenever you guys have a question. I'm gonna go, now this is, I've updated this slide just barely. There's this applet that used to be on a website that I loved, and it has since disappeared. So this is the next best thing that I could find as far as an applet to show us what ANOVA is doing visually without getting too involved in the number crunching. Okay. So in this picture on my screen, there are these 4 orange blocks. These are supposed to represent 4 groups. So on the y-axis, we have this scale from -10 to +10. We're comparing for these 4 groups, and they've labeled the groups W, X, Y, and Z. So right now, these groups are identical. Would you say yes? Now let me move one group. So here, I'm moving the W group. Notice the W group is now higher than the other 3 groups. Now it's got several things represented here. In each of these orange boxes, which represents like that group's scores, there is a solid burgundy line through the middle of it. The burgundy line through the middle of each of these groups is the group average. This dashed line here is the grand average. So I can hover on it, it says grand mean. And then if I go on each group, here's group W, this would be the mean of group W. So what's K in this picture? K is 4 groups. Yeah. So I can use these sliders to make each of the groups have a different average, and I can use this bottom set of sliders to make each group have a different standard deviation or a different spread. Okay, so I'm gonna make it so you can't see what's down here. There, I want you to tell me, are these groups the same, or do you think these groups are different? What would you say? The same. They should be exactly the same. Here. Oh. There. They should be, they're exactly the same. Okay. Now let me change them a little bit. Are these groups the same or different?
They're about the same.
They're about the same?
It's
Leah,
probably not statistically significant.
well, let's ask an easier question. Are they identical?
No.
No, they're not identical. But do you feel comfortable saying that they're different? What about now? Are the groups the same? Are they all the same? No. Okay. Let me see. Let's. Let me. Here we go. Okay. Are these groups the same or are they different? I'm not saying are they identical, but is there evidence that at least one of these groups is different? Now, if we look at those burgundy lines through the center, are the group averages different numbers? Yes. But what do you notice about the spread? These groups,
It's about the same. The spread
they
is the same.
overlap a good deal, right? There's a great deal of overlap. So would you say these are the same or evidence that there's at least one difference? Same or at least one different? Everybody give a thumbs up or down. Thumbs up means they're all the same, essentially. Down means there's at least one group that's different. Same? Same?
I don't know. I can't really tell if like Z's average is above the box of X.
Yeah. Okay, so should I make it a little easier?
Yes.
There. Okay. They're the same, right? Is everybody comfortable saying there's not really strong evidence that there's differences here? Okay, but what happens now? Would you say those groups are the same or at least one is different? Ryan, you're quiet. At least one difference? What happened? What changed?
The lowest mean falls below the spread of the others, like doesn't overlap.
Okay, here I have not changed the averages at all. The average group averages have stayed the same. Here we have a lot of spread within the groups. So the groups look very similar. But when I change the spread, the averages stayed in the same spot, but now the groups look different. With an ANOVA, our job is to judge if the means are the same or if there's evidence the means are different. But how do we judge whether or not the means are different? We have to make that decision in the context of how much spread there is within each group. So this threw me off at first when I was first learning about analysis of variance. The name says variance, but we're comparing the group averages. So what gives was my initial take here. Why call it analysis of variance? Because we want to know, do the groups vary in their averages more than the groups vary within each group? So that's why the name is analysis of variance. So these red group averages are different, but how different makes them different? Well, it depends on the amount of spread in the groups. Now, check that out. What do you guys think about that one? Those of you that had a chance to read the chapter, what does this give any red flags in your mind about the assumptions?
Yeah.
I know some of you read the chapter because some have already done the discussion point. I'm not trying to call anyone out because it's not due till tomorrow, but I just wanted to point this out while we're here.
Well, it seems like the homogeneity of variance is different.
Yes, Melissa, thank you. Thank you for going out on risking it. Yes, this is called a violation of homogeny of variance. So in order for us to make this judgment call, whether the group averages are the same or different, we're going to assume that the groups have the same amount of spread. Homo means the same, variance, same spread. In this picture right now, there is not the same amount of spread. This group W has a whole bunch more spread than the other three groups. So this picture, if this was our data, would violate the assumption of homogeny of variance. I'm going to pull this up so we can see the rest of this picture, the applet. Okay, so I'm going to come back here. Let's make us have homogeny of variance again. Okay. All right, so there we have our 4 equally spread groups. Okay, down here at the bottom under these little boxish plots, we have 3 things being represented on a common axis. We have the mean squared between and the mean squared within. This is mean squared residual or mean squared variance. So this first one, MS between, measures how much the group averages vary. There are only 4 group averages in this case. How much variation are in the group averages? And this MS within, that's how much spread is within any one of the groups, assuming that they have the same amount of spread. It's the pooled variance, basically. So somebody said on the discussion point for this chapter about the APA reporting, why would we report MSE? MSE, or mean squared within, mean squared error, same thing. It tells us how much spread there is inside of each group. It's basically the pooled standard deviation or pooled variance measure. So here, there is spread within the groups. Now watch this yellow amount, the mean squared within, what happens to it when I make the groups more spread out. So I'm gonna take my sliders and all 4 of my groups, I'm gonna make them more spread out. I'm not gonna change where they're centered at, I'm just gonna make them more spread out. What one of these colored bars changed? The mean squared between or the mean squared within?
Within.
The within, mean squared within, translate or captures how much spread is in each group. And I can bring that down. Let's make them all the same to simplify things. So the spread within a group is the mean squared within. The MS between is how spread out the averages of the groups are. So right now, how different are those group averages? They're not very different, right? Remember, the group averages are the dark magenta or the burgundy or maroon lines inside each group, and then the dashed line is the grand average. Now, what if I do like this? Now check out the group averages. The groups are spread out. How much spread is there between the group averages? MS between, that's a lot bigger number. So the way the ANOVA works is we make a ratio or a fraction. And on the top, we put the mean squared between, and on the bottom, we put the mean squared within. And when we calculate that fraction ratio to decimal number, that's our F ratio. So if I go back to having the groups all have the same center, what's the top of my fraction if the groups have the same center? It's essentially 0. If all the groups have exactly the same center, there's no variation between the group averages and the grand average. So the top number on our fraction is 0. So it doesn't matter what our mean squared within is, our F ratio is going to be 0. Now, if we have a little bit of variation in our group averages, well, we're going to compare it. Right now, what has more variance? Is there more differences between the groups, or is there more variation within the groups? We don't have exact numbers, but we have these bars to kind of show us. This teal bar on top, that's the mean squared between. That tells us how much these 4 group averages vary. And this yellowish middle bar, mean squared within, tells us how much the scores inside of each group vary. So here our ratio is a small number. What would I have to do to make my F ratio grow? This purple or bottom bar. How could I make that F ratio grow? There's at least two different ways.
Wouldn't you need to make the MS between bigger?
How would I make the MS between bigger?
Change the means more?
Make the means more different? Ooh, now what's our F ratio? like 30-ish. It got bigger. This purple bar got bigger. So one way to make your F ratio grow is to have your groups have much different averages. What's another way to make our F ratio grow? If we don't make the top bigger, we could
make the bottom of the ratio smaller, so the MS within needs to get smaller, so smaller spread.
smaller spread within each group. Yep. So the F ratio is made up of two components, the mean squared between and the mean squared within, and both of them can change the F ratio value. Now, as a researcher, you don't always have control over these things, but I just wanted to show you mathematically what the relationship is. So let's deal with an example, shall we? Everything's more concrete with an example. I believe this is the example in the textbook. Is it? Someone recognize it? So we have a study that wants to know if the amount of noise in a room inhibits or affects learning. So to do this study, we have 15 participants and we're going to put them in 3 groups, randomly assigned. So the way we would use our letters is we usually use the capital N in APA to be the whole sample size. So we have 15 total participants. Sometimes in our mathematical formulas, this is N with a little T subscript, T for total. But in APA, we'd use a capital N to be the total sample size. We're going to divide our total sample of 15 into 3 groups. Then we know K is equal to 3, and little n is our subgroup size, is 5. In this case, K equals 3, we have 3 levels to our independent variable. And those are, once we get our people assigned to our 3 groups through either flipping a coin, rolling a dice, or doing a random number generator in a computer program, the people that end up in group A, we're going to have them memorize this list of words. Everyone's going to memorize the same list of words and be quizzed on it 15 minutes or 1 minute after 1 minute of memorizing it. But the 3 groups are going to be different in that the noise in the room that they're sitting in is going to be different. In group A, there's going to be no music. They're just going to be sitting in a quiet room, just quiet. Group A is quiet. Those that got put in group B, when they're memorizing this list of words and they're 15 nonsense words, they have 1 minute to do it. They're going to be in classical music. This is the moderate noise group. And then the third unlucky group of people, I guess, they're going to have 1 minute to memorize these 15 nonsense words, same list, same time, but they are in really heavy rock music, very extremely noisy. So our independent variable is the grouping variable. Our dependent variable is our interval ratio numeric outcome score. And this one is going to be how many of those 15 words they memorized. Now, is number of words out of 15 really continuous? Is it truly interval ratio? We could debate that all day long, but we're going to go with it, okay? So we're going to have the same steps of a hypothesis test that we do in all hypothesis tests. We're going to state a null and alternative hypothesis. We're going to calculate our test statistic. Now we've done Z and T. ANOVA is going to be F. And ANOVA is going to still 1 and 2 tail. We usually do 2 tail. Choose our alpha, 0.05. Then we're going to get our sample, collect our data, find our rejection region, see if we are in the rejection region or not, what's our degrees of freedom is important there, and make our decision. So the steps we're going to use are the same steps we've used before for different hypothesis tests. There we go. All right, so to do this, we have multiple groups. For each group, when we get our data, we can calculate an average and a variance / standard deviation. There are, oh, I don't like this. This is all overlapping. That's not fun. Okay, well, so we got means and standard deviations. Our null hypothesis is that all the groups have the same average. Now, when we write our null hypothesis, we always do it in terms of the population, the whole population, not just our sample, but we write the null hypothesis is that all the groups have the same average. So that's mu1 equals mu2 equals mu3 equals however many mu's we have. And our examples thus far in class today, they've all had 3 groups because that's the simplest one to deal with. And it's the most common. It's important to know that our alternative hypothesis is not that all the groups are different. The alternative hypothesis is that at least one of the groups differs from the other groups. This is why it's called the omnibus. It's just looking overall, is there any evidence that any of the groups, at least one? So this is important when we're writing our conclusion. Off a little bit. Okay, so here's the data as it's presented in the book. A, B, and C's numbers are side by side to make this table fit in your book really nice. But is the first number in column A, that 8, is that 8 partnered with the 7 in the middle column and the 4 in this column C? Are those connected in any way? They're not. They're not repeated measures. They're not a triplet that were matched, nothing like that. So when we put this data in, we want 1 line per person. And so we want it stacked up like this. Now here I've done furniture table 1. Now it's handy, we haven't done the group by command on the furniture table 1, have we? I don't think we have. Here is a really cool, if you do dplyr group by a variable before you do table 1, it will summarize by group. So you can get the averages and the standard deviations for each group one at a time instead of just the overall sample. So if we look at group A, the number of words that those 5 people memorized were 8, 10, 9, 10, and 9, an average of 9.2 words. And here I've made a side-by-side box plot. And then the second group of people, these were the ones in the classical moderately loud music. They averaged 6.6 words. And those group C with that heavy loud music, 6.2 words on average. Eyeballing it, what are your eyeballs telling you about these 3 groups?
They are different.
They are different. What do you mean by they? They're all different from each other, or at least one is different from each other?
At least one is different.
Which one do you think is different?
A.
A looks to be
Significantly higher.
have a significantly higher number of words memorized on average compared to
B and C.
B and C. And it looks like B and C are roughly the same, right? That's the eyeball test. Now we need a statistical test that proves it, that gives evidence to that conclusion. So we're going to create an F ratio. And the top is mean squared between, and on the bottom is mean squared within. It's this idea that we have a fraction. And the stat is stuff we can explain with our variable divided by stuff that we cannot explain with our variable. Mean squared between, mean squared within. So your book had a lot of fun formulas, didn't it? Did you guys appreciate these fun formulas once you got to section B? Melissa, I know you loved it, right? Yeah, it's just doing some mathematical algebraic comparisons. The main idea is what's in this green box down on the bottom left. You can algebraically prove if you have 2 groups, your T statistic squared will be your F statistic. F is a T statistic squared. That's where it comes from. So Fisher, Ronald Fisher, Sir Ronald Fisher, he published about the F distribution, this ratio mean squared between, mean squared within. And he showed that the F statistic is always positive. It's a one-tailed distribution. So on the previous slide, I said, where was our hypothesis steps? one tail or two tails. With an F-test is always two tails, or always one tail. There is only one tail. Because it's a one-tailed distribution. It gets more normal with a bigger sample size, and the mean is approximately 1. 1 is the fraction number when the top and the bottom are the same, roughly the same, so mean squared within and mean squared between. So it's a family of distributions. All of these pictures here are F curves. This top one is, now T distributions only had 1 degree of freedom. F distributions have 2 degrees of freedom because they have a degrees of freedom for the numerator and a degrees of freedom for the denominator. Let's see. Got it right. Okay. So you're going to have 2 degrees of freedom. This first picture is when both degrees of freedom are 1. Numerator degrees of freedom 1, denominator degrees of freedom 1. What do we name this? What name do we use for this shape? Do you remember from like chapter 1?
Like a negative skew.
It's even more than that. We would call it a J distribution. Oh. Yeah. So this upper right-hand corner is degrees of freedom 3 and 10. This bottom one is degrees of freedom 10 and 10. And this last one is 10 and 100. So as the degrees of freedom get bigger, it moves away from being a J-shaped to being skewed to moving over to become more normal-ish. Okay, so we're gonna go fast through some of these. So all we need to know is whether the variation among the group means exceeds the variation within a group. It's that fraction. Okay, so, oh, it's not gonna show unless we go into this. Okay, so here's our formula for T. We take our group averages and subtract them. Now this is some data. You guys see this data for drug and placebo. So different data than we've been looking at. And this is data we looked at a long time ago, drug group, placebo group, and its T statistics was 1.96 with a p-value of 0.085. So it wasn't statistically significant. But the way we did a T, this is one version of the T statistic. And we can plug in our means and we can plug in our standard deviations to pool. If we do this, we get T squared, all of this squared, we end up with an F value. If we take our T 1.96 and square it, we get our F value of 3.84. The whole purpose of this example is to prove that an F value is just a T score squared. So assumptions. Do these assumptions look familiar to anyone? Yes? I hope so, because they're very familiar. Independent random sample from the independent variable. How do you ensure that you have an independent random sample? Well, you plan ahead as best you can. If we have an observed pre-existing condition, we want to randomly select from each population. So Brian, if you want to compare veterans to currently employed people to retired people or something like that, you'd want to get a random sample of each of those populations. And it would be probably take a different process to get those 3 different samples. You'd have to sample one way to get a representative sample of your veterans, and you'd have to get a different pool and a different sample for currently working individuals, and on and on. So you'd have to do different sampling procedures to get your 3 different simple random samples. If we're doing an experiment, we want to take one sample and then randomly divide it into the different groups. We want to ensure that there's no connection between the subjects in the different groups. It would not be okay to take family units with a mother, father, and child and make those the 3 groups and treat them as independent groups. Now, what did we do before? We said their husband and wives or parent and child. We couldn't do a regular independent groups t-test, but what could we do if there was a connection between the 2? Not an independent groups t-test, but a
matched or paired.
Matched or paired. Laura, I saw your lips moving too. A matched or paired. In ANOVA, today we're learning independent ANOVA, but there is a repeated measures ANOVA that's like for matched pairs or matched triplets or quadruplets, but we won't learn that till like chapter 14 or 15, but just know it's there. Today we're doing independent groups. So we want to make sure that the subjects in each group are independent of each other. Now, another way you can do pre-existing conditions, you could go take a random sample off a voting list and then ask them, were you a veteran, were you not, to get your groups, and that works, and those are considered independent subsamples, but the problem is they're going to probably be very different sizes. With an ANOVA, you want your groups to be as close to the same size as possible, and this is kind of a downer about ANOVAs. ANOVAs were developed in agriculture by Ronald Fisher when his groups were like plants. And he was, you know, they were crossbreeding the seeds, so they had complete control over everything, the environment. So there was no attrition. There was, you know, they could get equal sample sizes. There was homogeny of variance. Some of these assumptions do not always hold a lot of the times in human subject design research, which is why ANOVA by itself is not probably going to cut it in all of your research. But it is the foundation on which we build all the other methods. So that's why it's important to start with this class, even though this might not be the be-all, end-all research method for you. But so we're going to have these independent groups. That sounds familiar to the t-test. The only new thing is we can have more than 2 groups. We can have 3 or 4 or 5 groups. Our outcome, our dependent variable, should be normally distributed in each group. I'm going to add that here. In each group. It's not, the assumption is not that it's normally distributed when you collapse everyone, but it's normally distributed in each of the groups. Now, if your groups are large, then it's not a big deal because the central limit theorem takes over. If we have smallish groups that are not normally distributed, they're skewed, say we're doing income and income is skewed, there are some alternatives to ANOVA like the Krusko-Wallis H test, which we're not going to learn in this class, but there are other methods out there that you can use. And then the third assumption is familiar from the t-test. We are assuming that we have equal spread in all of our groups. And because they're equally spread, we can pool the variance, and that's the mean squared within, which is also called the mean squared error, or the MSE. The way we're going to test this is with Levine's test, which, how do we test for normal distribution in each group? I guess we should talk about that. How do we test that? Test normality.
Don't we do like, I mean, we can visually graph it out to show it like a QQ plot or, yeah, a histogram.
We can, yes, I totally am a proponent of the histogram QQ plots to determine normality. There was also another test that we learned quite a while ago. Does anyone remember it?
Is that the Shapiro-Wilks test?
And I probably spelled that one. The Shapiro-Wilks test. And that was for smallish samples. And there's the other one, Sam. I'm doing great on spelling today, aren't I? Okay, so I would usually go with the plotting. How do we make sure we have homogeny of variance? Levine's test. Have we done Levine's test before? You betcha. Is there anything really new on here, this slide? There's not really anything that's very new here. The new thing is we're applying it to not just 2 groups, but 3 or more groups. The concepts are exactly the same though. If we have small samples, the homogeny of variance test, Levine's test, can be underpowered. So usually we use our own judgment to whether the spreads are approximately the same. The same thing with normality. How do you judge normality? Sometimes you have to use your judgment and your knowledge on the things that you're studying. If we have one of these things violated a little bit, your results are probably okay, but you want to state the violations so that everybody can be aware, to be transparent and for reproducibility. However, if you have large violations or multiple of these things violated, then you have a risk that your p-value will be inaccurate. And there's no stat police that are going to jump down from the ceiling and say, freeze, you can't do that. You as the researcher have to check the assumptions first. Now, for our class, I'm going to have you write about the assumptions in your APA results, and we're going to talk about them. But once you move out of this class, most people don't write anything about these assumptions in a journal article unless there's major problems. And if there's major problems, then they have to do some other method. So we will get in the habit of writing that we check normality and use Levine's test to check homogeny of variance. But just know when you're reading your journal articles or you're writing up your own journal articles, you're probably going to cut that sentence to fit the space that you have available. I would definitely include this information in a dissertation though, because in a dissertation, you're proving to your committee that you know what needs to be done. And so it's okay if you use extra words to make that point. So I would definitely include this checking assumptions in a dissertation, even if it doesn't make it through the edits of a journal article because we only have so much space. I feel lonely today. We all doing good? Quiet today. Yeah, there are lots and lots and lots of formulas in this chapter, right? There are versions of each formula for whether you have an equal sample size or an unequal sample size. All of these formulas will be available to you on like the test. That's when we're concerned about these things, right? On your formula sheet. So let's look at the formula sheet. So we've done this front side that had the t-tests. And then on the back side, it had effect sizes and Pearson correlation. This post hoc test, this comes after ANOVA. So this is our next chapter. On Wednesday, we'll talk about this chapter about post hoc tests. But here we have the one-way ANOVA. The formulas for most of the things we talk about are here on the back or on this side of the formula sheet. So all of the effect size measures and the formulas are here that you'll need. Degree of freedom trees. So you don't feel like you have to memorize these. Maybe print these out so that you can refer to them and learn where things are, but don't feel like you have to memorize all of these stinking formulas because there's a boatload that the book feels impressed to press on you. Okay. Okay, so let's go back to our example. Here was where's our example? Our noisy memorizing words, this example, right? So we're gonna make our F statistic. Now, you can do a one-way ANOVA by hand. You can do it. And the book has you do, or the homework has you do one or two. But in the real world, if you have more than this size of a sample, this will drive you bonkers with arithmetic errors. And so we're only gonna do a couple by hand. Very unlikely you have to do this by hand on the test. It's more likely, what will I do for the test? What have I been doing? I will give you
the code
and output and ask you to
analyze it or interpret it.
Interpret it, yeah. But let's go through some by hand, just enough so that we can trust the formulas that the book spits out. Okay. Go here. So here is the summary table from this data. Group A, Group B, Group C. They're all the same size, which makes all our mathematics easier. So here are our group averages. So to do the F statistic, first you have to do the mean squared between. What is the difference between the groups? We have three groups. How different are their averages? So the first step is we have to find the grand average. We have the group averages. And remember on our little diagrams, these would be the maroon box averages. And we want the grand average. That was like that big dashed line. How do you find the grand average from the 3 group averages when they're the same size? What, Melissa? Oh, not me.
Oh, you just average them.
Just average them. So add them up and divide by 3. So the grand average is the average of the averages. Okay. Then we want to know what's the standard deviation of the means. So we have to take each of these 3 means and how much they vary from the grand average. So we're going to take the grand average and subtract it off each group average, square it so that we get rid of negatives, and divide by, well, usually when we're averaging, we divide by 3 because there's 3 groups. But because we're doing SX, the standard deviation, S, instead of the population, sigma, we divide by K minus 1, the degrees of freedom, 1 less than the number of groups. And this is to get the unbiased estimate of standard deviation. And we talked about unbiased standard deviation way back in, what was it, chapter 3? When we do the divide by n minus 1 instead of the dividing by n. So you take each
Sarah?
of the, yeah.
So in number 2, the left side, the notation there is the variance. I'm trying to figure
the variance. Yeah.
the variance of the means.
Yeah. So this, if I do this, so I subtract the grand average, square them, add them up, and divide by, in this case, 3 minus 1 is 2. And this is SX bar squared. This is the variance. So if I want the standard deviation, what do you have to do?
Gonna take the square root of it.
Got to take the square root of it. So MS, the mean squared are variances. So sometimes the MS are called the variances, so they're variance components. So we're going to leave the S squared and not do the square root. And so I said here find the standard deviation of the means, but really we're doing the variances. So that was a good call. You called me out on that. Good job.
I just wanted to make sure I understood it correctly. I was thinking, what does that square mean?
Yeah, the square means it's the variance and not the standard deviation. That's a good call. Now in that box, it says MSB is equal to little n times SX bar squared. So see the formula for MS between has S squared. So that's why I'm leaving this S squared, the variance, not the standard deviation. Now I'm supposed to times it by little n. What is little n? I already put it up here. Was 5 your first guess? It might not have been. Who thought maybe to put 15 there? That's a common mistake because we have 15 people in our study, but little n is the group size. 5, 5, 5. Now the formula is a lot more complex if the groups are different sizes. Thank goodness our example by hand has the same group sizes to make things simpler. So these are the 3 steps to find the MS between. This is going to be the top of our F ratio. Now we need to find the bottom of the F ratio, which is the pooled sample variance. So the top of our F statistic is the variance in, there it is. It's the variance in the sample means multiplied by the sample size. Okay, so we did this one. So now we're going to do this one. So first thing we have to do is we have to find the average of the variances. Now in our summary table here, do we have the variances? Not exactly. What do we have? We have the means. We just use those to do the mean squared between. But what do we have? What are these numbers that are in the parentheses? They're the standard deviations, not the variances. So we are going to have to square those before we average them. Oh, lovely. They're supposed to be squaring them. They're off. So we square each of those averages, add them up, and divide by 3. We're averaging the variances. And that's the mean squared within. If your groups are the same size, the mean squared error, the mean squared variance is just the average group variance, assuming that they are all approximately the same. Are those 3 variances identical? They're not identical, but they're same-ish. 0.8, 1.5, and 1.6. So we square them, add them up, divide by 3, 1.9. This is our mean squared within to go on the bottom of our F ratio. Okay. So we get our mean squared between and our mean squared within, and we make our fraction, that's our F ratio. Now, here I've drawn a picture. What do you notice about these three groups? Where are the three group averages? Exactly the same. Notice, what is the shape of each of these groups? A normal curve. Our assumption is that we have normal curves within each group has is a normal curve of the outcome. So if we fail to reject, that's saying that the groups are essentially the same, or we have no evidence that the groups differ in terms of the average. And this is when our F ratio is around 1. If our F ratio is bigger than 1, that means the top of our fraction is bigger than the bottom. So there's more separation in group averages than there is spread within groups. And the way that would look is if our groups have different averages so that there is separation in our groups. So if our F ratio is close to 1, we fail to reject the null hypothesis of equal group averages. If our F statistic is bigger than 1, then that tells us that there is more spread between the groups than there is within each group. Now, we've done what is often called the summary stats method, where we plugged in averages and standard deviations on the previous slides. That's the better one to do by hand. But the computer is doing the sum of squared approach. So it's doing sum of squares. We've talked about these several times. So it's going to partition or divide the variance in much the same way that we did for regression. Remember, we took the sum of squared total and divided it by sum of squared explained and sum of squared unexplained. It's the same partitioning or dividing. Our total variance is going to be that which is between groups versus that's within groups. The between groups, how are the groups different? Whatever is the designation of groups. Within a group is just person-to-person variation. So the total variation is going to be split up into that's between and that's within groups. So we've got degrees of freedom that go with each sum of squared. The total sum of squared, total degrees of freedom. Total degrees of freedom is the total sample size minus 1. Group sample size between groups is number of groups minus 1. And within groups, the degrees of freedom is total sample size minus number of groups, k. Sometimes this is called our partitioning of degrees of freedom can be called a degrees of freedom tree. And there's one of these drawn on the formula sheet. With a one-way ANOVA, it's fairly simpler compared to what it's going to get. We just have one grouping factor and the rest is error. We just have two piles. Sum of squared that it's explained, sum of squared that's unexplained. Between groups, within groups. We just have two piles. Okay, here's a picture of our F table. So the F table is in the back of your book after the Z table and the T table, and there's one on power and there's one on correlation. I can't remember which one is it. Which one is it? It's back there. Now you need to be careful about this F table. There are 3 different pages with F tables on them, and you have to look at the picture at the top of the F table. So this F curve is drawn and shaded on each one, and there will be a little alpha equals published right here. This one is for alpha equals 0.05. The next page looks almost identical, but it says alpha equals 0.025. And then the third one says alpha equals 0.01. You really want to be careful that you get the right page when you go to look something up in the book. Okay? So the way you read this table is you have to know both degrees of freedom, the numerator degrees of freedom and the denominator degrees of freedom. There's sometimes labeled DF1 and DF2. The numerator first degrees of freedom is the number that's across the top of the page. This is the K-1 groups. Down the side is the denominator degrees of freedom. This is the total sample size minus K. So for the example we just did with the 15 people divided into 3 groups for the music, there are 3 groups, so what's the numerator degrees of freedom? 2. So that would be the second column. And there are 15 participants, so how many denominator degrees of freedom would there be? 15 minus 3 is 12. Yep, so we'd go 12 and 2, and our critical value would be, well, 3.89. This table gives you the critical values that you have to be beyond to judge statistical significance. Okay. So the one we just looked at, the first degrees of freedom would be 2, because 3 groups take away 1. Our second denominator degrees of freedom would be total sample size 15 minus 3 groups, K, is 12. Now, we did the math, the mean squared between was 13.267, and the mean squared within was 1.7. How do I build my F statistic? What number goes on top? The mean squared between. What number goes on the bottom? Mean squared within. And if we divide them, we'll get our F statistic. Now, this is often called the observed or calculated F statistic. This is what we get from our data. Then we have to go to the table to find the F critical value. So we went to our table and we said 2 and 12 degrees of freedom, our critical value is 3.89. Now, what's our conclusion? Our critical value, that fence that we have to make it beyond, is almost 4, but we observed a test statistic of almost 7. What's the conclusion?
Reject the null hypothesis.
Reject the null hypothesis. And what was the null hypothesis? What did nothing going on mean about these 3 groups?
They all
No
have the same.
difference in the group means.
No difference in the group means. Memorizing words doesn't matter what music or noise is going on. You're going to memorize about the same number of words. That's the null hypothesis. We can reject that. So the conclusion, now it's very careful about how you write the conclusion. The F statistic is just an omnibus overall. So we can only say at least one music or noise level has a different mean number of words memorized. We can't say that all 3 groups have a different average, just at least one of the groups has a difference.
So Sarah?
Yeah.
Once you are able to reject the null hypothesis and you know that at least one mean differs from the rest, would you go back and start doing t-tests, or how do you find out where the discrepancy is?
You are so on, you're just right on track, Laura. That's
Okay.
the next chapter. And we
Oh.
do t-tests. But instead of going back and doing t-tests like we used to do, you do a t-test. It's called a post hoc t-test, and it's like a subset, or we use the ANOVA. What we do is we use the mean squared within as our estimate of pooled standard deviation instead of going back and doing a t-test with just 2 groups. And it's more powerful that way. Now, there are some other extra stuff you have to do, to the point that it's a whole separate chapter, because there's some things you have to be careful of. So that's what chapter 13 is on.
Okay.
Yeah, it's the post hoc test. Post hoc means after the fact.
Okay.
Yes, and that is true, because you can't just stop there and say, at least one group's different. My job is done, go home.
Just like, I've never read these results in an article, like, oh, we found there was one difference. We're not going to tell you what it is.
Exactly, exactly. You are so correct. But we're only gonna go that far in this chapter, and then the next chapter we'll take it. We're only gonna bite off this much in this chapter. So for this chapter's homework, that will be your conclusion. At least one group is different, period. And then after we do next chapter, you would never stop. And so after Wednesday, you'll never stop at that spot again. But just for right now, we're gonna just stop there.
Okay.
Yeah. So let's see how we do this in R, shall we? Because this one was fine. We could do this one by hand. It was nasty, but we did it. In real life, we're going to do it with R because easier. So the group, you group by a grouping variable, and then do table 1, and it will give you what we call as stratified descriptives. So one of our prerequisites or assumptions is Levine's test needs to be ran to check for homogeneity of variance. Now, we did Levine's test before. It's in the CAR package, Levine test. The formula is the same way we've done with all of our t-tests. The continuous interval ratio outcome we're comparing, tilde wave, name of the grouping variable that divides them. The only thing is here now our grouping variable doesn't just have to have 2 groups. This Levine's test will work if your grouping variable has 10 groups. And data equals dot to pipe it from above, and center equals mean to fix that wonky default. And it will give you Levine's test. Now I want to point out on Levine's test. Levine's test is an F statistic, but what are the degrees of freedom for this one? 2 and 12. They're the same degrees of freedom that you're going to get for your F test, but be careful. This is the Levine's test. This is testing for homogeneity of variance. Homogeneity of variance. I can't highlight it on here. So it's just the same as the t-test, outcome tilde wave grouping variable, homogeneity of variance test. So what is this one telling us, this homogeneity of variance test? Do we meet the assumption? Do we have no evidence of violation, or do we have evidence of violations?
No, we should be good because the null of that is that all the variances are the same.
The null hypothesis for Levine's test is nothing going on. The variances are the same. You're good to go. And we failed to reject that, so we can keep going.
So as long as that's over 0.05, we're good to keep going.
Yeah. Now, if it's less than 0.05, it depends on how much you'd want to look at the, how big are your groups? Is it really, is it a judgment that I can make that, yeah, this time they're not equal, but it's close enough. But generally speaking, we look at the p-value for Levine's test, and if it's bigger than 0.05, we're good to go forward. If it's less than 0.05, ANOVA is not right for us.
So are we looking at this PR?
Yeah, the PR greater than, this is saying the probability that we observe F greater than or equal to this F number.
Okay, and we want that to be greater than 0.05.
We want, in this case, for Levine's test, we want it to be non-significant because that means there's no violations. Okay, are you guys ready to see the code for an ANOVA?
Mm-hmm.
Okay, we're going to use this code for every single day of this class from here on out, except for the very last day. And let me just preface this with, this is one thing that drives me crazy with SPSS and SAS and Stata, is that you have a different command for one-way ANOVA, for two-way ANOVA, for repeated measures ANOVA, mixed design ANOVA. They're all different commands. Tyson and I searched to decide which command to teach you in R to do ANOVA. There are at least 20 different packages and functions in R to do ANOVAs. There are a ton of them. But we chose this one because it's the same layout, same syntax for every kind of ANOVA you could possibly do. So we're going to make your life easier. Okay? Here is the command. So let's break it down. Here we're saving it to something called fit ANOVA. But so that's our saving, but notice we start with our data set and we pipe it in, and this is the package is here coming first. The package is AFEX. It's for analysis of factorial experiments is what it stands for. I didn't name it, somebody else did. And instead of saying the whole word ANOVA, it's only AOV and then _4. And the reason it has the number 4 is because the way that this works, the syntax matches the LME4 package, which is the most well-known and well-used package for doing multi-level modeling. And I don't know why Bates called it LME4, probably because it was the 4th version, was the one that worked the best and stuck or something, I don't know. But we're gonna use the AOV4 to mimic that syntax. And we can use it exactly the same for all of our different kinds of ANOVAs we're gonna learn.
Hey, Sarah, I'm sorry, just right above that, that fit _ ANOVA.
That's the name we're going to store it as.
We're going to store it as that name, and then the name of the data set in this is DF, but ours might be data clean. It might be.
Yeah,
Okay.
it might be memory long, you know, you whatever your name of your data set is.
Okay, thank you.
Name of the data set piped into AFEX AOV4. And the first thing that comes in here is our formula. Let's see, how does this formula compare with the formulas we've done in t-tests and Levine's? Ooh, we're starting out good. We start with the continuous interval ratio score we're comparing, tilde wave group, the name of the grouping variable, but we have something new tagged on at the end that we have not seen before. This is telling this in parentheses, it has to be in parentheses, the number 1 vertical bar ID. That vertical bar on your keyboard is above the enter key. It lives on the enter key with the slash on it between enter and backspace or delete, depending on your keyboard. That vertical bar, the way you read this, it says, the parentheses tells us we have 1 observation per, the vertical line means per ID. Today we're doing independent groups analysis, which means that we have only 1 observation per person. We will eventually get next week to where we have multiple observations per person. So we have a repeated measures design, and we'll put something that's not the number 1 there. But for now, it's kind of just like a placeholder. We only have 1 observation per ID. And this just makes it so we can use the same function for independent groups and repeated measures, and we don't have to learn something new every time we turn around. And then after the formula, we have to say data equals dot to pipe the data from above. Syntax looks very familiar to the CAR and the CAR-Levine's test and the t-test commands, right? So it looks exactly like a t-test, except for we have this parentheses thing hanging out on the end. Now I've saved it as a name because with the ANOVA output, we almost want to do multiple steps after we run the ANOVA analysis, because the ANOVA is just the omnibus, and we'll want to do things like post hoc tests afterwards. So here I've fit it, and I've called it fit ANOVA. If you run just the name, you get this abbreviated output. Do you remember when we did the LM, the regression, the linear model, and we piped on summary to get more full output? There's a way we can get more full output out of our ANOVA command, but we don't use the summary. The way we do it is we do a $ and the word ANOVA, A-N-O-V-A, all lowercase, at the end of the name of the model, and that will give us more full printed, more output spit out. It's not necessarily different output, it's just more information, a more informative table. So doing the $ ANOVA, now this one says capital ANOVA, I think it's capital ANOVA. It gives you some more information. Now there are some slight differences, I don't know why they have. This one, it says type 3 with the numeral 3. This one says type 3 with the Roman numeral 3. I don't know why it's different. But we have the 2 different ways of spitting out the output. Now for both of these, oh, where's my pen? It's right on my screen. Okay. Oh, don't go on. What would our F value be on both of these? Can you guys find the F value?
So there's the 0.54, but is that the p-value?
Yeah.
Oh, F value is down here.
Let me see if I can get it here. Okay. Let me draw on it. Yay. Okay. All right, so let's look at it here. So it doesn't line up exactly perfectly here. This is the p-value.
Okay.
So p-value goes here. So our p-value is 0.010. This number 0.54 is the GES. The GES is the generalized effect size, or the eta squared. then what's this 6.98? That's
That's your F.
that's our mean squared error, or mean squared within.
And then the 1.90?
Wait, no, that's your MSE. Your MSE is
Yeah, you're right. You're right. F comes first and then mean squared. It's hard when we print it out in R, it's usually lined up. Here that changed the font, and so it's like tilted.
Got
So
it.
let's see. P, GES, F, mean squared error, and there's your degrees of freedom. So let's see, how many degrees of freedom does our F have?
2, 12.
2 and 12, we get two numbers for degrees of freedom. So we go F 2, 12 equals 6.98, and our p-value is 0.010. Now I want to point something out here. When you ask for this $AOV and you get this full table over here, the first line always says intercept. Always, always, always ignore the intercept line. This is testing assumption that the overall average is 0. The grand average is 0. It's almost never of any importance. It always spits it out. There's no way to get rid of it that I know of. So you just ignore. Ignore the intercept line. So we still have our F value, and there's our P value. This one right here, this is sum of squared within. So this way gives you your sum of squared. This one gives you your mean squared error, or mean squared within. So they give you different things to a point, but both of these give you your F degrees of freedom and your F value and your P value. Those three things you can get from either type of output. On this one, where do we find our degrees of freedom? Our degrees of freedom are stacked up right there. And then there's our F value and our P value. This one's nice, this full one, because you get sum of squareds, which are nice for some formulas that we have to use by hand. This one's nice because it gives you your effect size, your eta squared. So a lot of times I'll do both kinds of outputs, the plain name and the plain name with $1 ANOVA on it, to get both bits. Okay. Here I plotted it. Now let's look at my code. I did the name of my data set, typed it into ggplot, aesthetics. My grouping variable is my x-axis, so it comes first. My continuous interval ratio score is second. And then this is what I added, stat_summary. And what it does is it puts a point on each group average and it makes little lines the standard error. If you were to look at this, which group is different? A is higher, B and C are about the same. So this is another plot that can help you judge, because if you do your F statistic just tells you at least one group's different. A plot like this can help you work out which group it is, and then we'd want to do t-tests to compare that group A is really higher than B and C are not different than each other. Okay, so most everyone that I read through on the discussion board were kind of okay with ANOVA, but a lot of times there came up again and again, the effect sizes. Who feels effect sizes are not great? Should we take a 10-minute break and then come back to the effect sizes? We've got, how much do we have left? We've got effect sizes and some power. Yeah, let's come back to effect sizes. So let's take 10-minute break. Come back at 5 after.
Sarah, I have a really well done question probably.
Don't say such things.
Well, it's true, but I guess I'm just, if we look back at page, slide, it's,
Oh, with the code? This one?
yeah, with the code.
Yeah.
So you said in that Carl Levine, there's the outcome and then there's the groups, and you could put all the different groups in there.
Well, group is the variable. So let's see, look at the way the data set, I'll show you how the data set's entered. It's how the data set is entered. Right here. See, the outcome variable is one variable, but see the group variable has
Oh,
A's, B's, and C's in it. Whereas before we just had A's and B's. We'd only have 2 levels to that factor. That factor can now have 3 or more values in it.
so do I have to do something to name those different ones?
It's how the data has been entered.
Okay, so then when I come down to the Fit ANOVA test where it says group, I'm just really saying the independent variable.
Mm-hmm. Yeah,
Okay.
the independent variable will just have more than 2 values, more than 2 factor levels.
But I don't have to put the 2 different ones in there.
No,
I-
the data will already be stored that way.
Okay, that's what I wanted to make sure of, sorry.
Yeah, no, that's this very applicable question because it matters. Yeah.
Well, thank you, that helps me. I was trying to just clear that up.
Hey, Sarah, if you are okay to talk, if not, I can catch it after class. I have a quick question for you.
Yeah.
Actually, I don't know if it's quick, but I'm having a hard time getting my R assignment to knit for this one. For some reason, I keep getting an error, which is not cool. And one error was that a package that we have installed doesn't exist. And so I did remove that package from the code. Was I supposed to?
That LS means?
Yes.
Yeah, that's defunct now.
Okay, so I did remove that, but it still wouldn't knit.
Okay, let me stop sharing my screen. I want you to share your screen with me and we can, because my guess is if you're having an issue, somebody else is gonna have the same issue.
That's something I was worried about too, and then to take out that line about the LS means, which I did. Now, where's my little share? Oh, there it is.
No, I have to stop share, I think. Did I stop share already?
I think yes.
Okay.
Do you happen to see it?
Yep, I see it. Okay, so yeah.
So should I just try and knit it right
I
now?
did it. Yep, let's see it in action.
If
Now,
I just click that, would it automatically do it, or?
You can, yeah, you don't have to do the drop down on the knit button. You can just hit the knit button itself because it already says output equals PDF document.
Oh, right there.
Uh-huh.
Okay, and it does this, and then I get an error and it says it stops.
Okay.
Now, if it does it for you, you have those magical abilities like my husband that technology works when you're around. Doesn't work when it's just, yep, it works. See? It's just you. Never mind. You just magically made it work. I don't know why I was getting errors. That's really weird.
You know, sometimes it just does.
But it did. There it is. It's just you. You just have a magical touch. See?
Can you scroll down to the packages loading the second chunk?
Uh-huh.
There you go. Okay. Do we have everyone back? Pretty close. Okay. So this is a change to the R code. It used to be there was a package called LS means and a package called EM means. The LS was for least squared means. The EM was for estimated marginal means. They basically mean the same thing, but they were packages made by two different groups of people, and they had a lot of the same functionality, but they weren't totally overlapping. So we used to have both packages to get everything done. Now, as in the last year, about a year ago, the LS means package is now defunct and removed from CRAN, I believe. And so everything's been moved over that we need into the EM means package. But on the R skeleton, you will still see both of them being loaded. You'll see library for LS means and library for EM means, and it won't run. It will complain about LS means. You can just delete the whole line that has LS means on it. Make sense? On here, so you'll have tidyverse, read Excel, furniture, our new analysis of factorial experiments, AFEX. EM means is for doing the post hoc test, and so is multi-comp. We won't really use them till the next chapter, but they're on here just because it used to all be one skeleton and now we're chopping them into chapters. So you don't really need either one, but it doesn't hurt to load them. So Kimberly, have you already gone and put all your answers in for the Canvas assignment for chapter 12? Okay. Shoot. I was going to add some intermediate steps to make it more places to check your work, but I don't want to screw up if you've already. Shoot. I just won't do it then.
There was some, I mean, it was good. It was a good homework assignment, but like, I felt like it.
Was it in long or?
It took a long time to get it done though. Holy crap.
Yeah, that's what I was afraid of. Now, the good news is we're only doing one chapter a day instead of 2 or 3. That's good news.
Yeah.
Yeah. So if we can get through the slideshow, we can start on it together. Wouldn't that be great? Okay, I gotta go back and share my screen again. Okay. Our last thing we need for this chapter, besides how to write things up APA, is effect size. So just because we have declared something to be of statistical significance does not mean that there is a difference that is of practical implication. And that is where we're going with effect size. So once we have determined that there is a difference, how big is that difference? Is it something that is meaningful or is it small enough that who cares? So that's the idea of effect size. There are at least 4 different effect size measures that you can calculate and publish for an ANOVA. And they're all used in different ways and for slightly different problems. The most common effect size measure for an ANOVA is an eta squared. And it's called eta, and it's the Greek letter that looks like a little n, but the last part of the n hangs down further with the square. It's called eta squared. Eta squared is the most common, probably because it was most frequently available in SPSS. SPSS spat out eta squared very easily, and the formulas for eta squared is very simple. But the eta squared formula calculation is a bias estimate of the so eta squared is supposed to capture the amount or the percentage of variance in the dependent variable explained or accounted for by knowledge of the group membership. So it's a percent variation explained measure, but it's based on in the samples. Eta squared is based on the samples. Well, it's supposed to be about the population, but it is biased when you use the sample statistics. So a more accurate, unbiased estimate would be omega squared. And it looks like a W, but it's really curly. That's the Greek omega squared. Omega squared is what we should be using because it is less biased. But a lot of researchers are unfamiliar with it because it does not automatically get puked out by SPSS. And there's a lot of researchers that if SPSS doesn't give it to them, it doesn't exist. So the good news is the eta squared, and even though eta squared is biased, it is not too bad. And it usually turns up if your eta squared was like 0.20, omega squared is usually like 0.19 or 0.21. They're usually pretty close to the same number. And that's why this has gone on for as long as it's gone on and nobody's made a stink about it. And so when you publish an ANOVA results, we almost always will publish the eta squared for the effect size, even though omega squared is probably a better estimate. But the formula gets really messy for the more complex ANOVAs. Another way you can measure effect size with ANOVAs is with a Cohen's F. Cohen's F I see very, very rarely published in actual application, but Cohen's F is the measure of effect size that G-Power uses. And so this is about the only useful thing about Cohen's F is that you need it to be able to use your G power for power analysis. Another measure is called the intraclass correlation. It has a lot of applications. It's the rho. We've seen rho for correlation before. It is used more when we have repeated measurements and not when we have independent groups. But it is used for those repeated measure or mixed design ANOVAs. So you'll see it. So the little red box here is telling you omega squared is less biased and probably better, but eta squared is probably sufficient in most cases. So eta squared tells you the percent reduction in error or the percent of variance explained by the grouping variable. And so you calculate it. This is why it's so easy to calculate it. You take the sum of squared between and divide by the sum of squared total. Very easy fraction to make. And so that's why this more complete output gives you the sum of squareds. Once you get the sum of squared numbers, you can divide them to find you take the total sum of squared by adding up both of those sum of squares, 26.53 and 22.88. Add them up together, you get the total sum of squared, and you divide the between groups sum of squared by the total, and that will give you your eta squared. Now this output actually tells you it's 0.54, it's done it for you. So the way we would write this in a sentence or speak it in a sentence would be 54% of the variance in words recalled is due to the type of music played in the room. 54% of the variance in the outcome, what was the outcome here? It was words recalled. So 54% of the variance in words recalled is attributable to, how were the groups determined? That was based on the music that was played. So 54% of the variance in words recalled is attributable to the noise or music in the room. Or 54, or the other way to say it around, you could twist the sentence and say 54, noise in the room accounts for 54% of the variance in words recalled. Not everyone remembered the same number of words. Some of it's because some people remember better. Some of it's because of the music played. And what's the balance? 54% of the variance is due just to the music that was played. What about the other almost half of the variance? It's due to everything else between what everyone had for breakfast and how good they are at memorizing random words and if they have dyslexia and every other possible factor that could be out there that we didn't measure with those two things, type of music and then words recalled. So it's a percentage reduction or percent of variance explained by. Now, if you have the sum of squareds, you can do it that way. If you have the mean sum of squared, you can do 1 minus mean squared within over mean squared total. It's just another mathematical version of it. This is the adjusted eta squared. Adjusted is probably better, but we don't use it very often. If you're doing a meta-analysis or a lit review of older articles, and they haven't put their eta squared, shame on them. But they did tell you the F statistic and the degrees of freedom. You can calculate what the eta squared was based on just the degrees of freedom and the F statistic that they do report. So this is like a backdoor formula if you don't have all the information and all the data, but you want to calculate the eta squared that wasn't printed in an article. And there are some kind of rules of thumb, which are very, very vague and shadowy for what we would call small, medium, and large effects. Generally speaking, so ours was 0.54. That's very large in terms of an eta squared. If your eta squared is 0.14 or bigger, that's a large effect in most social science research. If your eta squared comes out to be between 6 and 14%, that's a moderately medium-sized effect. Now, these kind of cutoffs for small, medium, and large, they depend on if it's a one-way ANOVA or a two-way ANOVA. So this is for one-way ANOVAs. That's all we're doing. We're only doing one set of groups. So here's our noise and words example. I've done it here with the sum of squared between divided by sum of squared within, that's sum of squareds approach. And over here, I've done it with just the F statistic and the degrees of freedom. Both ways it comes out to be about 0.54, just what the R output said. So on the R output, it's labeled as GES. GES stands for the general eta squared. It's just plain eta squared. In a one-way ANOVA, there's only one eta squared. When we get to the more complicated ANOVAs, there's multiple eta squareds. Where's our formula sheet? Here's our formula sheet. So here in the formula sheet, so for one-way ANOVAs, we just have one way we're grouping our participants. There's our ordinary eta squared. That's ordinary or generalized eta squared. Sum of squared between groups divided by sum of squared total. And here's the modified or adjusted eta squared. And here's the estimated omega. Can you see that the omega formula is a lot more complex than the eta squared formula? The omega squared is more accurate. It's not as biased, but again, in most situations, they come out to be close enough to the same number that we don't worry too much about it. But look, when we get down to two-way ANOVAs, there's more eta squareds. There's ordinary and partial. And when we get down to mixed design ANOVA, there's lots of kinds of eta squareds. But when we do our independent or one-way ANOVA, there's only one eta squared really. It's just the ordinary or general eta squared. Okay. There's that formula sheet. Okay. All right, so here's the omega squared. The same cutoffs apply, it's just a more complicated formula. You don't need to memorize this formula, it's on the formula sheet for you. I'm not gonna really make this a big deal, for it is, omega squared truly does only range from 0 to 1. Eta squared should range from 0 to 1, so that's why it's a percentage, but sometimes it can be wonky when we get more complex. But you can think of eta squared as a percentage or between 0 and 1. And there's a kind of our cutoffs for them. So Cohen's F. Cohen's F is a little bit more complex. Cohen's F, you can compute if you know the omega squared. So a lot of times we do two steps. First, we'll calculate the omega squared, and then based on the omega squared, we'll calculate the Cohen's F. If you don't want to stop in between, you can go straight to Cohen's F by doing this formula, which is the square root of junk. And the top of the junk is k minus 1. What's k again?
Your groups, number of groups.
Number of groups. On the bottom, it says n little j. Little n with a little j. Little n is supposed to be the group size, provided all the groups are the same. If the groups are not the same, you have to do the harmonic mean of the sample sizes. We'll just say that. All of our examples are either going to be done in R, so it does it for you, or it's going to be same size groups, so you don't have to worry too much about that. And then we've got mean squared between, mean squared within. And here's a formula if you have the Cohen's F squared and you want to go back to omega squared, so converting the opposite direction. So you can move, if you have one, you can find the other. They're just a reformatting of the other. It's the Cohen's F is a generalization of the Cohen's D. I'm not sure why the G power makers decided to go with Cohen's F. I don't find it to be used in a lot of other places, and it causes a lot of confusion. I have a lot of people coming to me to do power analysis for ANOVA, and they don't know what Cohen's F is. But it's not a measure of association, it's a measure of effect size as far as differences in groups. So the last one, here's the interclass correlation. There are at least 6 different kinds of interclass correlations. We're not going to get into it a lot, but I just wanted to mention it. Let's see, this is about the end of it. Let's wrap up with the methods and results section, how you would write these things up APA. There's no one right way. You're gonna want to at least tell the reader what your variables are, like what's your independent variable, what's your dependent variable, how many groups you have, did you do a power analysis, did you meet the assumptions, and then what's your conclusion. So in this one, it says a one-way ANOVA. Now this is the example we've been using throughout. A one-way ANOVA, you need to say what test you're gonna do, was used to test the hypothesis that the means of the three groups, or that the type of music, were different following the experiment. That's our alternative hypothesis, is that they're different. The alternative hypothesis is just that at least one is different. And then the sample size analysis. Now this part here, we didn't do it here. We were just given the data because it was a toy example. But in real life, you should be doing power analysis before you gather data, unless you're working with extant data, where you're limited to what you have is what you have. But sample size analysis conducted prior to beginning the study indicated 5 participants per group would be sufficient to reject the null hypothesis of at least 80% power if the effect size was moderate. Cohen's F equals 0.95. Cohen's F cutoffs are different than eta squared cutoffs. And then the results. Results indicate significant differences among groups. Now, what part numbers did they put at the end of the sentence? We have our F value with both of its degrees of freedom in parentheses. We have our P value. Now, it should be P is equal to 0.010 to 3 decimal places. I'm going to change that. Now, here is reported an omega squared, but you could report an eta squared as well. Some people suggest also putting in the mean squared error, and I think our book does, right? I don't usually put in the mean squared error, but you could. If you were going to put the mean squared error, I would make, does the book say to put it first or second? Does it say first? I think it has it precede the F value. I don't have my book on hand. Now, just like Lara said, usually we would not stop here, right? If we're going to say at least one's group is different, we would follow it up. But for this chapter today only, we are going to stop there. Next chapter, we will figure out how you follow that up to say which groups are indeed different.
On the assignment, Sarah, how do you, because I don't think in the assignment boxes, I don't think we can do math formulas. So like, is it okay if we go N caret 2 for the assignment?
Yep.
Okay.
So anytime on the assignment and you're writing APA, they're just plain text boxes. So anytime you're supposed to put like an omega squared or an eta squared or any of the, or rho or any of those Greek letters, just do the English letter that's the closest to it. And then for a caret or for a power of 2, you can just do the caret, which is the shift key on the 6. And then if it's a subscript, you could do an underscore. I'm not going to worry too much about that. I mean, maybe I should go back and allow for all that, but we'll just keep it simple. Keep it way simple. So you can put W with a 2 by it even, or if you're going to do eta squared and little n with a 2 by it, and I'll know you mean eta squared. Okay. So this is kind of leading into the next lecture. I kind of want to.
Hey, Sarah, I found that in the homework, the write-up, and they do the F and then the MSE and then the p-value.
Oh, that's weird. So Barry Cohen in our textbook suggests putting the mean squared error after the F statistic, but before the p-value. Okay. I would probably have put it before or after keeping the F and the P together, but I don't know of any APA guidelines for that.
And the same thing with the eta squared, put that between the F and the P.
I would say I almost always see the eta squared after the P value. I would make that change. I would, and on the homework, if you've already turned it in or something, I wouldn't worry too much about it, but I would put the effect size after the P value. Now there is some discussion on this point. Should you put an effect size if it's non-significant? If your conclusion is no evidence of a difference, No evidence of a difference. Should you put an effect size measure?
I mean, does it really matter? Because if you have no evidence, I mean, it would be really weird to have no evidence, but then your eta squared being big. Like, that wouldn't make any sense. So it's almost contradictory.
No significant difference, but a big effect size. The only way for that to happen is if you had a really small sample size, which can happen in pilot studies and dissertations. I am of the persuasion, if your p-value says no significant difference, no evidence of a difference, you don't need an effect size. That's my take. But in general, there's a feeling in social sciences, you put the effect size no matter what to inform the audience that it's not just a sample size issue. Because if the effect size is small, then you know it's not because the sample size was too small, that you failed to get statistical significance. So it's never going to hurt you to report an effect size. It might be something you might have a conversation with your mentor or your co-authors or journal editors about. It's something that's not clear cut right now. Mathematically, I feel like it's no effect, don't put an effect size. But when we can sometimes fall into small sample sizes where it could have been significant if we'd had a bigger sample size, and we don't want readers to think that we just, didn't do it correctly, that if you show that there's not statistically significant and the effect size is small, then it like puts everyone to bed.
So with our author using MSE equals whatever, like, why would you report that? Like, what is that telling your audience? To me, that's just what is that saying? Like, why would you want to report that?
That is helping establish how much spread is within each group. It's like the group-wise variance. I would much rather publish a plot, is my feeling. I will always go for a plot instead of that.
So it's just saying, hey, this is how much variance on average the subgroups had.
Mm-hmm.
I don't know. That just seems like such a weird thing to report to me, but I'm with you. I'd much rather put a plot, but
that's why I don't see it usually reported. I'll usually see summary statistics, means and standard deviations for each group, like we get with furniture table 1, and then not putting the mean squared error anywhere. That's almost always how I see it in real life. Almost always. So do you guys want to get into the assignment together? Has anyone started it and have a question they want to start with?
I think my questions were on the APA write-up, which you're helping me understand how to do that.
Yeah. And with the APA write-up, remember there's not only one way to write it. And you can always keep massaging and editing it to flow better the longer you stay on it. And I don't want anyone to like waste time, but give it some time, because this is your practice attempts. Come on. There. Okay, let me go to student view. This is the great part about the second half of this class, is we get to slow down to where we can use more class time for assignment working. Okay. Start. Okay. Okay, we have 240 students. Yeah, this is a good size sample in a large introductory psychology class, and they're scored on an introversion scale, how introverted they are. They fill that out in class. And then they're divided equally. So based on where they're sitting, we have the front third, the middle third, and the back third of the lecture hall. Have you guys all taught a class before? Most of you guys have been TAs, right? Taught something. Do students sit randomly in a classroom when given the chance? When students come into the classroom, there's certain people that self-select the front, the middle, and the back. So this is looking into that. Now this is made up data, so make of it what you will. But we have 240 people, and we have the front, the middle, and the back. So here's a little summary table. We have the 3 groups, each of the groups' averages, and each of the groups' standard deviations. Okay, and here are a bunch of our formulas. So we're supposed to calculate the F ratio. So let's start with the easy bits, the degrees of freedom. How do we find the first degrees of freedom? The numerator degrees of freedom.
K minus 1.
K minus 1. And what is K in this situation?
3.
3. So our first degrees of freedom are 2. Okay. Cha-ching! What's the second degrees of freedom?
240 minus 3.
240 minus 3. Okay, filled out 2 of the 3 boxes without much hassle. Now this one's a little bit more. This is where I was going to add some sub boxes for checking your work along the way. We need to calculate the F ratio. The F ratio is where we divide the mean squared between by the mean squared within. So let's calculate the mean squared between groups. What do we need to do first? So we've got these X bar G, that's the group averages. We have those 3 group averages, or they're the X bar I, those are the 3 averages, I going from 1, 2, up to K3. We need X bar G. X bar G is the grand average. So the first thing we need to do is calculate the grand average. How do we calculate the grand average?
It's the average of the 3 group means.
The average of the averages. Does someone have that?
I think it's 33.4.
33.4. Can someone second the motion? Now what do we need to do? Take each of our group averages and subtract the grand average and square it.
Is it wrong to use your calculator on that and have it get the standard deviation of the 3 means? And then just square it?
Sure.
I got to work. And then I don't have to do it by hand.
Yeah. You don't want to do it by hand. Let's use R. I like R.
R is better than my calculator, yes, but.
Okay. So the means are 28.7 and 34.3 and 37.2, right? Oh, what did I do wrong? I got to concatenate my list. Okay, so I can ask, M is those numbers. So we can do, what is the mean of those means? 33.4, yes. Now I can take each of those numbers and minus 33.4, like this, there. And then I can take each of those numbers and square them And then I want to take all of that and add it up. Oh, what did the formula say? I'm lost the formula.
You're right. Now I think you divide by 2.
Okay, so let's see.
Is that right?
All right. Oh. What did I do? You go away. There we go. So I took each of those numbers, 3 numbers, subtracted this value, the grand mean average, squared them, added them all up, and what did I get in R? 37.34. Now I'm supposed to take the 37.34. That's actually, that's them all added up. Then I divide it by what number would be down there? K minus 1 is 2. Now, very careful. There's a little thing right there. I almost didn't see. What does it say?
So we got it times by how, I can't remember how many's in each group. 240 divided by 3.
How many was in each group?
240 divided by 3 is how much?
Capital N was 240. K equals 3 groups. So little n is 240 divided by 3. Calculator says
80.
80.
So, sorry, quick question. The X bar I
Yep.
minus the X bar G. Okay, what is the X bar I again?
Those are the group averages. So you're going to take each, so the summation says we're going to sum up when I is 1 to K. Remember, K is 3. So I goes from 1, 2, and stops at 3.
Oh, so the whole top half is just finding the average.
37.34.
Okay. Okay. Because I get the 33.4, but then how do we get from 33.4 to 37 point?
Oh, okay. So we'll write it down here. If I was going to write it all down,
Yeah.
I would take the first group average minus the grand average, square it.
Okay.
And then I would add the second group minus the grand average.
And then square that. Okay.
And then the third one. And that is what gets me the 37.34.
Okay. Thank you.
I just was lazy and used R.
That's great. No, I was just confused because I took the individual averages and minus the grand average, and then I got 0. And I was like, of course I got 0. Why did I do
You
that?
gotta square them first. Or
Yeah.
else if you don't square them first, it adds up to 0. And you're like, what the heck? That was like stupid, right?
Got it. Okay. Thank you.
Yeah. So did anyone get a number for this?
I think it's 1492.
I got something a little different. I got 1490 something different.
Don't know.
Did I? We're going to times that by 80, but divide it by 2. Oh. I got 1493.6. Did you try it again, Hillary? I mean, Melissa?
No, I didn't try it again.
You're gonna go with mine?
I figure you're more likely to be right than I am.
No, risky. Okay, so that number, that is the top of our fraction. Now we need to calculate the bottom of our F fraction. So to do that, we need to take the, what does the formula say? We take our standard deviations and we
Square them.
square them. Add them up and divide by 3. And let's keep 4 decimal places of our intermediate work. Did anyone get that one? Shout it out when you get it. We'll see if someone can second you. I only make you do this by hand twice. This is the first time.
I think it's 150.5633.
I got that exact thing. 150.5633. And that's the bottom of our F ratio. So how do we make our F ratio?
Numerator over denominator.
Numerator over denominator. So the 1493.6 divided by 150.5633.
$9.92.
Can anyone second that?
Yeah, that's what I got.
That's what I got too. So the next one, ding, 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 ding. Same thing, except for what if the standard deviations were twice as large? If the standard deviations were twice as large, what part of the F statistic would change? Would the top part change?
Just the bottom.
Just the bottom. Would the degrees of freedom change?
No.
No. So on the top of the fraction, we're going to still have 1493.6. It's just the bottom number that's going to change. There's our formula there. If you get the new bottom number, shout it out. Let's see if we can get it together. So you'll take your 3 standard deviations, 22.4, 24, and 27, square them each, add them up and divide by 3.
I got 602.2533.
Can someone second that?
That's just for the within group.
Within group, and I will say that is correct.
What was that? Because I'm trying to compare it to what I just got.
602.2533.
Yeah, that's what I got.
Awesome, 602.2533. So that's the new bottom number of our F statistic. The top number still stays the 1493.6. Oh, wrong mouse. There we go. So what would that make our F statistic?
$2.48.
So what was the effect on the F ratio when we doubled the standard deviation?
Decreased by like 4 times.
It got, did we multiply or divide by 2 or by 4? I can't get it all on one screen. Let's see.
The F ratio or the standard?
F ratio
Okay. The F ratio was divided by 4.
divided by 4. It went from being 9.92 down to being 2.48 because there's more spread in the group. Think about that app we did. If you stretch out the groups, they don't look as different from each other.
Mhm.
Yay. Our last one by hand. Is mental arithmetic affected by drugs?
Ooh.
Homework's never boring, right?
This is great. I love this.
Okay, get rid of that one. That one. Get rid of this one. Okay, so we have how many subjects?
32.
32. So 32 is what? What letter would we use for 32?
K?
Is it K?
No, sorry. No, K is the group. Sorry.
K is the group.
And
What's the N?
N, little n or capital N?
Capital.
big.
And to the with a T, subscript T.
N with a T, or we can use a capital N, either way. Okay. Capital N is APA, N with a little t is for the formulas because we get to do double duty as social scientists. What is K?
Four.
Elia, shout it out. We have
4.
groups. Okay. So they're doing as many problems as they can do in 10 minutes. We got those on marijuana, amphetamines, Valium, and alcohol. This is a great study. Okay, what do we, if we're doing this by hand, what do we need to do first?
Grand mean.
Grand mean.
Grand mean. How do we find the grand mean?
Add up all the means and divide by 4.
At least they did some nice numbers. Do you think this is real data?
No.
24 divided by 4 is
6.
6. Okay. All right. Now we're going to do, let's do our formula. So we're going to take, what's little n?
8.
How do you know it's 8?
The number in a group.
We're going to take our total sample size and divide it equally. So we're going to take our 32 total subjects and divide them equally into 4 groups. We're going to have 8 times something divided by what goes on the bottom of this fraction?
3.
Number of groups minus 1. And on the top, we're going to have, it says add it all up, okay, going from 1 to 4, the first group average minus the grand average squared, and then the next group average minus the grand average squared. Okay. So for the first group, how different is it from the average? 7 minus 6 is
1.
1 squared is
1.
1. Okay, that's nice. The second group, 8. How different is 8 from 6?
2,
2 squared is
4,
4. And then the next group, it's only different by
-1, but squared.
-1, but we squared is 1. And the last group,
-2, but then squared, that's +4.
so on the top of this fraction, we're going to have 1 plus 4 plus 1 plus 4 is
10.
10. So we've got 10 divided by 3, and it's timesing by 8.
So
80 divided by 3.
80 divided by 3.
26.6667.
And that is the
Numerator for your,
top or the numerator of our fraction.
yeah.
How do we find the denominator? To speed things up, I did this in my calculator. Is that okay? Can I tell you?
Yeah.
I'm going to square all of my standard deviation numbers and add them up. Divide by 4. 10.1089 to speed things up.
Okay.
So how do I find my F statistic?
The MS between over the MSW within.
$2.64.
2.64. Let's see. 2.64. Oh, we got to fill out our degrees of freedom. What's our numerator degrees of freedom?
So 3 and
4 groups. So 3 degrees of freedom in the numerator.
and then 32 minus
28.
32 minus 4 is 28. Okay, so now we're supposed to go to table A7 to look up the critical value. Let's practice this. There's the lookup tables. A7. So make sure you get the one where it says alpha 0.05, or else you will be wrong. You will cry. Right, Kimberly? You will send me an email and I'll be like, oh yeah, you already answered yourself. Okay, so what do we say our degrees of freedom are?
3 and 28.
So 3 is the first one, 28 is the second one. Oh, I didn't go down far enough. That's annoying. What happens if you don't see the exact number you need on the table?
Pick the closest.
Pick the closest. See, notice what happens after the number 30.
It starts skipping by
Start skipping because it's pretty much the same for a while. Just
Yeah.
very off by very few numbers. Okay. Be careful when you go across too. Okay, so what's our critical value?
2.95.
2.95. Oh, come back. Thing is just like to be my best friend. 2.95. What about the degrees of freedom? Those are the ones we use to find it in the table. Okay. So our critical value is 2.95, but our observed calculated F ratio is 2.65. What's our conclusion?
So I actually just did it and mixed it up and got it wrong. So
What could it be?
it should be that we failed to reject, because I was thinking that the critical value needed to be lower than the F ratio, but It's actually the F ratio.
We've got to get beyond the critical value to get in the rejection region.
Yeah.
Okay. So what would happen if we had double the number of subjects? What would let's look at the degrees of freedom. Would the degrees of freedom change? What would be the first degree of freedom?
Three.
It would be the same. What would be the second degree of freedom though?
Much larger.
Yeah.
60?
What would it be?
60?
60, because if we had a sample size of 64, and then it would be -4. For our F ratio, what's going to change? Is the numerator on top going to change? Look at the numerator's formula. Is anything about the sample size in there?
Yes.
Yeah, where does sample size get put in this equation?
That little n, so we'd have to take 64 divided by 4.
Yeah, we used to have 32 divided by 4, so we had 8 for little n. If we have a total sample size of 64, then our little n is going to be
16.
16, so that's double. So what's going to happen to the top number, the mean squared between? The mean squared between is going to be how much bigger?
Twice as big.
Twice as big. And what was it on part A?
So now it's going to be, on part A, it was 80 divided by 3, but now it's going to be 160 divided by 3.
Yep, instead of being 80 divided by 3, it's 160 divided by 3. So instead of being 26.66667, it's going to be double that. So it's going to be
53.33333.
53.333. Now, will the bottom of the F statistic change if we have a bigger sample?
No.
Because is there anything about sample size in the numerator or the denominator, the bottom number? No. So the bottom of the F statistic is still going to be the 10.1089.
Mine says that's wrong.
What did you put in?
Degrees of freedom, I put 3 and 60, and then I tried it twice, 53.33 and 53.3333.
It's 53.333 divided by 10.1089.
Oh, that's what I did wrong.
Yeah.
10.1089, that's right. Is this answer to 2 places?
Mm-hmm.
So 5.28?
5.28. Yes. So when we look it up in the table, we're going to look up 3. It's still the numerator degrees of freedom, but instead of the denominator freedoms being 28, it's now going to be 60.
Is this the same table that's in our book?
Mm-hmm. This is exactly the same one in your book.
I don't know what I did wrong. I found the wrong table last time.
Did you make sure it was the alpha equals 0.05 table? Because there's 3 pages. The next one says alpha equals.
I don't know what I found last time.
It's very easy to get the wrong one. Make sure it's the alpha equals 0.05 one.
So it's 2.76.
Let's see. Yep. Numerator 3 degrees of freedom and denominator 60, 2.53. But were we asked for that? Oh yeah, 2.53.
I think it's 2.76.
Yeah. Oh, wait. Yes, it is 2.76.
2.76, yeah. Yeah. So what happened? What is the effect on the F ratio of doubling the sample size? So
You
you got
divide by
the
2.
original one of 2.64 down to this one, 5.28.
Multiplied by 2.
It's double as big. Double as big, multiplied by. Okay, from now on, you never have to do that by hand again. Anyone want to do a little jig?
Hooray.
Okay, the next one we get to do in R. Shall we do it together? We have just
Yes.
time.
Yep.
Okay, so up here is the download for the RMD skeleton and the Excel file that you do not need to get again if you still have it from last time or the time before that or the time before that or any of the times before that. Okay, so like we said right after the break, you will never need the LS mean package. It's now defunct. And actually for this assignment, I don't think you need EM means or multi-comp, but it doesn't hurt to have them loaded. I think you only need these first 4. So here are our little data sets. So there's a wait time based on the calling. Is that the one we're doing here? Yeah. So social scientist wants to know how long people will wait before responding to the cries for help from an unknown person and whether the gender or age of the person in need of help makes any difference. One at a time, subjects sit in a room waiting to be called for an experiment. They don't know this is the experiment. After a few minutes, they hear cries from help, help, help from the next room, which are actually a tape recording. The cries are either in an adult male's voice, an adult female's voice, or a child's voice. 7 subjects are randomly assigned to each condition. The dependent variable is the number of seconds from the time the cry begins until the subject gets up to investigate who needs help. So there's the data set.
And we're supposed to take out the LS means?
Mm-hmm.
Okay.
Okay, so there's our data set. So here's the times, the 7 people, their reaction times, the 7 people that heard the child recording. In the middle are the 7 people that heard the woman calling. And the last 7 are the men that heard the recording. Oh, it has to go to, no, I already did this. We'll just run this. I'll update this for the next class. Okay, so this is wide format, but it really, the first number 10 does not go with the first number 17, does not go with the first number 20. They're not linked in any way. So we don't want it in wide format. We want it in long format. We want 1 line per person. And so here we have this variable caller type says child, woman, or man. This is our grouping variable. The delay time, that's the number of seconds it takes to get help. See how there's 1 line per person? Mm-hmm. This is how we need our data set. So to do this analysis, we're going to need data weight long. No, this isn't the skeleton. This is filled out. Is yours filled out? Oh, I filled some stuff out. Okay, on purpose. Okay. So here's the summary table. Group by caller type, do furniture for the delay. So here is our descriptive table by caller type. The child, let's see, eyeball, what do you think? Average 8.9 seconds. Man calling, average 16.1 seconds. Woman, average calling time, 10.9 seconds. Doesn't make a difference who's calling. Well, let's look at the standard deviations. What are the standard deviations? 4.5, 5.8, 5.1.
Not a huge difference.
I like to plot it. Now here's something if you might not have noticed. I have put output equals markdown inside of my table 1. That makes it so when I knit this to PDF, it makes a nice table in the middle of the page instead of having yucky looking output. But it makes it so if your cursor is in the middle of the page, you can't scroll. Very annoying. The way to get around this is to move your cursor over to the edge where the line numbers are, and then you can scroll down. Just a little trick I learned. Okay, so here's some side-by-side box plots. If we look at the side-by-side box plots, what does your eyeball tell you? Does it make a difference? Lara says yes. How so?
It looks like the male or the men's average doesn't overlap with it, either the children's or the women's.
You know, there are some overlaps because each of these points is a person, but the boxes don't overlap, the middle 50%.
Yeah.
So let's see. So here's another plot. This is the stat summary plot. Stat summary does the points that are the average and the lines that are the standard error. This looks separate, right? So let's do the one-way ANOVA. So to do the one-way ANOVA, we need to start with the long format of the data set with 1 line per person. What was that called? Data, weight, long. Now, if you don't remember what's in your data set, you can run it and it will print it out here so you can see your names of your variables. Now we're going to pipe it on to our AFEX AOV4. This is our command for doing all of our ANOVAs. AFEX :AOV_4. The first thing that needs to be in there is our formula. What comes first in our formula? Here. What comes first in our formula?
The outcome?
Isn't it the dependent variable?
The dependent variable, the continuous interval ratio measure we're comparing the averages of, which is called what in this one?
Delay time?
Delay time. The continuous interval ratio thing we're comparing. Then we have our tilde wave, and next is our
Color type?
Color type, the grouping variable, our independent variable, our factor. In this case, our factor has 3 levels. Color type. Because if we keep going down, we've got child, 7 lines with child, 7 with woman, and then the last 7 are with man. There are 3 levels in this one factor. Now, the next thing we need to put in there is data equals dot. Now, I've also not finished my formula. What's new about the formulas in the ANOVA? We have to add on a little bit there we've never had before. We have to add on some parentheses. And what do we put in these parentheses?
1 bar ID.
1 bar ID. We have only one observation per ID. And it's ID because that's what that column, the identification numbers, are called in this data set. What is it? It's not called ID in Eno's data set. Can you guys remember in Eno's data set what they call it? It's not ID, it's sub_num. So just be aware that's going to happen later. Now, if I run this, it will do the ANOVA, but we're supposed to fit it and save it so we can do some stuff. So we're going to save this as AOV wait time. Now, when you save something as a name, the chunk makes no output. But we do get this red, kind of scary looking message. This is fine. It's just telling us that color type is a categorical variable, and this is the default. Don't need to worry about this message about control sum contrast. That's fine. Okay, it says request the omnibus F value by typing the name you saved your fitted model to as above. That's all we need to put in this next chunk. And it will give us the basic ANOVA results. So on Canvas, we're going to have to put our F value with its degrees of freedom. What are the degrees of freedom?
Two and 18.
2 and 18. What's our value of F?
3.75.
3.75. Yep. So when we come into, let's see, if we go to the next one. Go to the next one. We're on item 3 now, right?
Mm-hmm.
Yeah.
So it's 2 and 18, and the F value was 3.75. From R. What do you guys think? Do you like to do these by hand better or let R do them for you?
R.
R. The critical value, you're going to look it up in the table, 2 and 18. 2 and 18. Critical value is
355.
3.55. So there's the null hypothesis. The average reaction time when the child calls is the same as the average reaction time when the woman calls, and that's also equal to the average reaction time when a man calls in the entire population. Do we have evidence against the null or no evidence against the null?
Against the null.
We do have evidence against the null because our observed F statistic is beyond or past our critical value, 0.55. And when you looked in R, did you notice the p-value?
Oh, it's 0.04.
0.04, 0.044. And check out our effect size. What's our effect size?
0.29.
0.29. How many decimal places should we use for effect size?
I think 2.
We're going to go with 2 just to keep things simple. That's usually sufficient. Do we need a 0 in front of this decimal on the effect size?
No, because it's between 0 and 1.
We don't, because effect size eta squared, it's a percentage. It's like a percentage, so we can leave it as without the 0 in front of the decimal. Notice with the AOV4 package, it does not put zeros in front of the decimals where they should not be. It's smart. So how would we write our conclusion? We're out of time, but if anyone wants to give it a shot before we go, that'd be great.
I do.
Okay. Are you ready, Melissa?
Yeah, I'm ready to have everyone help.
Oh, I thought you wanted to read yours.
No.
Does anyone want to read theirs before we sign off?
So we have to make reference to what kind of tests we ran. So we
Uh-huh.
ran the ANOVA, and it's only a single conclusion statement. So after running a univariate ANOVA,
And you can call it a univariate ANOVA, an independent ANOVA, a one-way ANOVA, whichever one of those phrases you want to say.
after running a univariate ANOVA on, what was it? How many subjects? 20 subjects?
21, right?
Uh-huh.
On 21 subjects, we can
Reaction time differed by type of differed for at least one type of voice. We don't know how to figure out which one it is yet. That's the post-op. Then we need our statistics. F of 2, 18 equaled, what did it equal? 3.75. So we take our F statistic. Usually after that, we put our P value. And at the end, our eta squared.
P-value was 0.044.
And that's a comma after voice.
Yep, and then a comma after the p-value. And then because this is only plain text, just do an N with a 2 next to it, or an N caret 2, and I'll know you mean eta squared.
So is that all we need to put for this?
It says it can be only a single conclusion statement. Must include the test statistic with degrees of freedom, p-value, and effect size if applicable. So what do you think about that effect size? Small, medium, or large?
I think it's large compared to what we looked at earlier.
Yeah, I think that Cohen's suggestion is a 0.14 is large. So
Yeah.
Again, it depends on what you're studying, whether that's exciting or not. A lot of human subject stuff, if your eta squared is even 0.02, it's exciting. It might not be large, but it's exciting. So here it had you do these by hand, but we know it's supposed to come out to be 0.29, which is strong. They're in random order. That is weird. Okay. Whose brain's fried?
It's kind of refreshing to do the basics again, but for ANOVA. I was just, maybe that's just me.
How do we get this next column? I'm unsure.
Let's fill in what we know. We know 2, and what were our degrees of freedom? 18. And we know our F is 3.75, and we know our p-value is 0.044. We know those things, right? The total line here at the bottom, the sum squared and the degrees of freedom total up. They add up. So for degrees of freedom, you just add down your row. 2 and 18 are 20. I've debated taking this one out because nobody publishes these anymore.
Well, where do we get the sum of the squares?
So if you go back into R, the plain output doesn't give them. But if we take our name of our model and add on $ capital A NOVA, it will give us our sum of squareds. Now remember that top line that says intercept, what are you supposed to do with it?
Nothing.
Nothing, ignore it. So there's your sum of squared for color type, 198.38. And then below it, there's the residual sum of squares, 476.57. And you can add going down. Now, if you were going to do the effect size by hand, you would need these sum of squareds. You would take the numerator sum of squared, 198.38, and divide it by the total, 167.95. But we have R now that tells it to us. The eta squared right up off the bat. Okay, just to be finishing this, and we're getting some bonus minutes today. The mean squared, both of these mean squareds numbers can be found by taking their sum of squared divided by their degrees of freedom. So the mean squared error, mean squared within, can be found by taking its sum of squared divided by its degrees of freedom. So 478.57 divided by 18 will give you that mean squared.
And we want all these to 2, right? To
Yeah.
2 places. So 26.59.
I got 26.48.
Huh. 0.57 divided by 18. 20. Oh yeah, 26.48. You're right.
Okay.
Something on.
I could be wrong.
No, figure you're not.
Top one we would, and in here, so 26.48, if you look at the R on the plain output, there's the MSE, 26.48.
Oh.
And then 198.38 divided by its degree of freedom 2 gives you 99.19.
And is this something we need to know how to do? Like, it's important for us to remember?
Yes and no. The more we use R, the less it's important, but it's still, they're important pieces to know. I think it's more important to know when to run an ANOVA and how to interpret the results, and when to be scared of running an ANOVA and know it's not the right thing to do based on the assumptions.
Okay. Cool.
The next question is almost exactly the same steps. So this should give you a good springboard to start into this assignment. Okay.
So discussion for chapter 12 is due tomorrow morning.
Mm-hmm.
And then the discussions for 13 and 14 are due Wednesday morning.
Now let me go out of student view. Just 12 tomorrow, midnight, 13 on Wednesday, 14 is not till a week from today.
Okay. Cool.
Yeah, we get to slow down a little bit in the pace of chapters. There are probably more meaty chapters is why. Okay. Well, you guys have more than, yeah?
Can I ask you a question after we're done? This is just my R is freaking out again. So I'm gonna come to our recording through on my other computer, so you have to let me in.
Okay.
Thank you, Sarah.
Okay. Thank you.
Thank you.
You're welcome.
So I'm trying to launch it right now. Hopefully it will. Where I'm having problems is on line 127. it pulls up just a white screen. So I'm going to come out of this now because it says it's connecting.
Okay. I don't see it yet, but.
Maybe I need to get out of this. Also, I'll get out of this one just so I have more bandwidth.
Okay.